Hello, this is Truth Socrates, and welcome to a portrait of linear algebra. So it's hard to believe we are about 3/4 of the way through this class, and today we are going to embark on the final module, the final unit of this class. And looking back, we have been working exclusively with vectors from Euclidean spaces, okay, Rn. So we worked with R2, R3, and then we generalized to higher dimensional Euclidean spaces. We talked about matrices, and we talked about linear transformations from one Euclidean space to another, and these were represented by our matrices. We talked about subspaces of Euclidean spaces. So today, we are going to ask you to open your minds to a different kind of vector space. In fact, many different kinds of vector spaces. So in order to create those new vector spaces, we're going to take a little look back first, all the way back to chapter 1. All right, so in section 1.1, I think that was our very first video, we saw a theorem which had 10 parts to it. Describing properties of vectors in Euclidean spaces. So we are going to use those 10 properties in order to create axioms for abstract vector spaces. So instead of a theorem, we will now think of this as a set of axioms. In other words, properties which we're going to believe are true, not exactly proved to be true, although we are going to prove it for specific examples. We are going to learn about several examples of common and very useful abstract vector spaces, and we will learn that many theorems that we saw for Rn in chapter 1 and chapter 2 will still remain true for abstract vector spaces. All right, so this is the theorem that I was referring to, which we found in section 1.1. The properties of vector arithmetic. If u, v, and w are vectors in Rn and Rns are any scalars, then the following 10 properties are true. So we saw two closure properties. We saw that vector addition is commutative as well as associative. We talked about the zero vector. Okay, there's a very special vector in every Rn. So when you add it to any vector, you'll get the same vector. We talked about additive inverses, also known as a negative. Okay, so if you have a vector v, you can find the negative for that vector v. How do you know you found it? If you add it to v, then you'll get the zero vector. And then we have these 4 algebraic properties. Okay, we have 2 distributive properties, one where you add the scalars and then multiply the vector, and one where you have 2 vectors and you multiply to 1 scalar. You have an associative property for scalar multiplication. If you now multiply a vector v, let's say by first s and then by r, or by first r and then by s, you'll get exactly the same answer. And both of those are the same answer that you get if you multiply v by the product of r and s. Okay, so in other words, these scalars R and S, they can move around. Okay, you can take it out here, you can take it out here, you can multiply them together, you can switch order. Okay, you can also write that as S times R times V, because multiplication of real numbers is, of course, commutative. And lastly, if you multiply any vector by the scalar 1, you get the same vector. Okay, so that's called the unitary property. Right, so what we're going to do next is we are going to take this theorem and turn it into a definition. Okay, so here are the 10 axioms that describe what is an abstract vector space. Okay, so as I mentioned, we need you to open your minds a little bit. Okay, so what do we start with? Well, we must have a non-empty set V, which of course contain our vectors. Along with that set, we must have 2 instructions. Okay, one set of instructions to define vector addition, how to add two vectors together, and another set of instructions to perform a scalar product, scalar multiplication. How do you multiply a vector by a scalar? Okay, but aside from just having those instructions, they must satisfy the 10 properties that we saw back in section 1.1. Okay, so I apologize that I can't fit it all into one screen. I thought of shrinking the resolution, but I'm just going to scroll back and forth. Okay, so the first two properties are again the closure properties. Add two vectors in V, you will still get another vector in V. Multiply a scalar by R, a vector by scalar R, you still get a vector in V. Okay, so the first thing you'll notice is that why is there a circle around the plus? Okay, why is there a circle around the times? Okay, so those circles, I kind of like to think of them as like training wheels on a bicycle. Okay, we're going to need them for just a little while. In fact, we're going to lose them in the next video because we just want to remind ourselves that we're not just adding vectors in Rn anymore. Okay, the addition might be different. The vectors will be different. Okay, so we also have the commutative and associative properties. It doesn't matter if you add u plus v or v plus u, you'll get the same vector. If you're adding three vectors, it doesn't matter how you group two of them first before adding the third, you'll get the same answer. Okay, now this is why I couldn't fit it into one page, because we now have to talk about the zero vector in a special way, okay? Because we're given this non-empty set of vectors, right? In Rn, we knew exactly how to make a zero vector, just put zeros everywhere, okay? So each abstract vector space has to come with its own zero vector. Okay, so we write it as 0 sub v, or just 0v, instead of 0n. Okay, but again, its property is very similar to 0n. If you take 0v plus any vector v, you'll get the same vector v. Okay, and of course, you can change the order by the commutative property. Okay, every vector also needs to have an inverse, a negative v. So notice that we also put a circle around the negative sign, okay? That really does not look natural at all, okay? But again, we're going to get rid of it in the next video. Okay, so what is so special about the negative v? It also has to be a vector, obviously. And if you add negative v to v in any order, you should get the zero vector, okay? The zero vector that we were talking about in axiom 5. Okay, the rest of the 10 axioms, 10 properties, are exactly as we have in section 1.1. Just the notation is different, okay? So you have a distributive property, multiply a single vector by a sum of two scalars, r plus s. It's the same as r times v, added to s times v, okay? You can add two vectors, u plus v, and then multiply it with scalar r. You would get the same answer if you multiply each vector by the scalar r, and then add the two vectors, resulting vectors, together. You have an associative property for scalar multiplication, okay? And this one deserves to look at very closely. You have v multiplied by s, and then that answer multiplied by r. Okay, the s can go outside and join the r, but when you multiply them together, notice there's no circle dot there. That's just ordinary multiplication of real numbers, r times s. Okay, and again, you can write that as s times r. We know that multiplication of real numbers is commutative. Okay, or you can multiply v by r first, and then by s, and all of these give you the same vector. Okay. Finally, when you multiply any vector by the scalar one, you'll get exactly the same vector. So what has to happen is that if we are given these vectors and the two instructions, how to add two vectors, how to multiply a vector by a scalar, it is now our responsibility to verify that all 10 properties in this checklist are verified by the set of vectors and the two operations. Okay, fortunately, our first example is going to be very natural. Okay, so we know about Rn. We're going to make this vector space called Pn. Okay, P stands, of course, for polynomials. All right, so Pn is the set of all polynomials p of x, which can be written as some constant c0 plus c1x plus c2x squared, all the way to cn x to the n. All right, where these constants, c0, c1 through cn, are all real numbers. Okay, so let's take these two examples. Let's have p of x is 7 minus 3x minus 6x squared. Q of x is 4 plus 5x minus x squared. Okay, so their highest degree is 2. So we can say that both of these polynomials are from the vector space P2. I was about to say Euclidean space. No, this is now a completely new vector space. So we call it P2 in this case. We have these two polynomials from P2. Okay, the highest degree is 2, so we can say these are from P2. Okay, do we know how to add two vectors in P2 together? Well, if you took algebra, you do. So we are going to add them just like how we did in beginning algebra. So in other words, add the corresponding coefficients together in the two polynomials. So 7 plus 4 is 11. Negative 3 plus 5 is 2x. Minus 6 minus 1 is minus 7x squared. Okay. Do we know how to multiply a polynomial by a scalar? I hope so. So if you multiply p of x by 3, you're going to get 21 minus 9x minus 18x squared. Okay, great. So what about all of those properties? Okay, commutative property. Does it matter if we add q plus p instead of p plus p? I think we'll get the same answer, right? Associativity. If you add three polynomials together, yeah, it works, right? Okay, let's talk about the zero vector. Okay, if I just made this 0 p2 for now, okay, what would be the zero vector in p2? Okay, so it still has to look like this, correct? But let's see, I wonder who the coefficients are gonna be. Okay, well, I think, okay, so remember the property is, if you add it to any polynomial, you should get the same polynomial. Okay, so I hope you can read my mind. That's just 0 plus 0x plus 0x squared. We see zeros appearing. Okay, so that is kind of natural because the zero vector in Rn simply had 0 in all the components, right? But we're not in Rn anymore. We're in P2, but of course, if you generalize now to any Pn, well, I think all you have to do is to keep going. So add more terms, and each coefficient will have to be 0. That seems natural, right? Okay, is there a negative, an additive inverse for every polynomial in Pn? Okay, well, we have these examples from P2. Okay, which polynomial, when you add to px, will give you all these zero coefficients. Okay, -7, whoops, wrong line. You should be over there. -7 plus 3x plus 6x squared. Yeah, if you add this to p of x, you will get all zeros. Okay, so I hope that feels very natural to you. Okay, what about the other properties? All right, so do we have a distributive property? Yeah, p of x times r plus s. Yeah, we know that from basic algebra, right? If you have p plus q times r, you will get p times r plus q times r. Assertion value, yeah. Multiply a polynomial by 1, you will get the same polynomial. So yes, Pn, where the vectors are polynomials of degree at most n, and vector addition is just addition of polynomials as we learned in basic algebra, and scalar multiplication is also just multiplied by constants. And we have a zero vector and an additive inverse for every polynomial, and the other properties work. Okay, so a polynomial, of course, is a special kind of function. Okay, we know how to take powers, we know how to multiply and add numbers together. Okay, but we can, of course, deal with other kinds of functions, right? So here is a vector space. It will be written as f of I, and it's made of all the functions f of x, so that f of a is defined for all a in this I. Okay, what is this I? It's a subinterval of the set of real numbers. So it could be all real numbers, that would be the simplest case, or maybe it's just 0 to infinity, or 0 to 1, or -3 to +5, or maybe 0 to 2 pi. Maybe we can do some trig. Okay, so if the domain, this interval I is our domain, if that domain is all real numbers, then here's an example of one function. Okay, and yes, it is made up of 3 functions, isn't it? Okay, more of that later. Okay, here's another function. And yeah, you can check that every term in these 3 expressions are defined for all real numbers. Okay, so do we know how to add 2 functions given f and given g? How do you add f and g? It's just f of x plus g of x. Okay, how do you multiply a function by a scalar k? Yeah, you just multiply the output by k. Okay. All right, so we know how to add these 2. Okay, it's going to have 6 terms. Okay, we know how to multiply f by -2. Okay, you'll get -2 of this, plus 8 of this, minus 18 of this. Okay, so again, it's the same thing that we see in algebra, or maybe in this case, pre-calculus. Okay, all right. Zero vector. So when we talked about polynomials, we had this special polynomial. Okay. Now, what's another way to think about this very special polynomial? Does it matter what x you plug into this, right? Whether it's 3 or 3 million to the 100th power, whatever that number is, doesn't survive very long because you multiply it by 0. Okay, so whatever number you input into this polynomial, the output is 0. Okay, so because of that, we are going to give this polynomial a special name, which we'll write as z of x, z for 0. Okay, so that is the 0 polynomial. Okay, we know the graph of polynomial, right? Well, if it's not too complicated, right? You know how to graph quadratics, for example. Okay, what does the 0 polynomial look like? It's not very interesting, but it's still a graph. It still has a graph, okay? The y value, the output is always 0. So it's just your x-axis, okay? So in the same way, when we talk about these function spaces, we're going to use the same symbol, okay? So it will be the function z of x, okay? And what makes z of x special, no matter what x you input, as long as it's from that interval, that output is 0, okay? But of course, yeah, this definition would work no matter what interval you're working with, okay? It could be all real numbers, or it could just be from 0 to 1, okay? All we want is that the output is always 0 for any input x. Okay, how about the negative of a function? Okay, do we know how to get the negative of this function? Yeah, you put negative here, plus 4x to the 7, minus 9 sine of x. Okay, so what about the other properties? Let's go back. Is addition commutative? Yes. Is it associative? Yes. Oh, let's not forget closure. Okay. If two functions are defined on the same interval, their sum is defined on that interval. Okay. Hopefully that sounds familiar. Remember that was one of the requirements that we had for linear transformations when we're adding t1 plus t2. Okay. Similarly, if you multiply a function by any scalar, the domain doesn't change, right? So it's still defined on I. Okay, we have associativity. Yeah, we talked about our zero vector, the negative of a function. Are these algebraic properties still true? Yes. It works for polynomials. There's really nothing special about polynomials. They're just functions. Okay, so therefore, f of I is also a vector space. So again, while we're taking this nostalgia trip back to section 1.1, we saw what vectors in R2 look like. Same diagram. Okay. We also saw what vectors look like in R3. Same diagram. Okay. Now what about vectors in P2? Okay. Or in this case, what do I have? I saw that 3x squared. I saw that 2x minus 5. But check it out. If you multiply these three together, you get a third degree polynomial. So these three vectors are from P3. Oh, wait a minute. The caption says 4. That must be a typo. Nope. There's another function hiding in the picture. See how the x-axis is kind of colored green there? Guess what? That's the zero vector, the zero function. Okay? So that's one main difference in how we visualize vectors in abstract vector spaces. We are going to concentrate on function spaces and in particular polynomials. Okay? Those will be our everyday playthings, our toys. Okay? When we talked about R3, okay, we said that the zero vector is just the origin. It's not an arrow, it's a dot located at the origin. The zero vector here in P3 is not a dot, okay? It has a graph, a very boring graph. You can barely see it because it's the x-axis, okay? But it still has a graph. Okay, so do I have more? Oh, yes. Here are some more exciting functions. And these are now from the vector space of functions defined over all real numbers, minus infinity to infinity. Okay, so I included a cubic because, again, we said polynomials are functions too. Okay, so we have 3 examples of functions defined on all real numbers. You have an exponential function shifted down. Okay, so you see it over here. And you see a horizontal asymptote. Sure. 2 sine 1/2 x, some trig. Okay, so the period is that pi or 2 pi? Wonder. Okay, so that's only 2 pi over there. So yeah, the period should be 4 pi. Okay, and we have this polynomial, so this cubic, and you can see it's zeros. Here's the cubic. You have a 0 at -4, at -1, and at +1. So it looks like that polynomial. Now, remember when we talked about subspaces in Rn, and we said that there are 2 trivial subspaces of Rn. It's the subspace made of only the 0 vector, 0n, and the subspace made of all of Rn, each and every vector in Rn. Well, what if we focused on the first trivial subspace? Okay, so we said in the 10 axioms that whatever set of vectors you have, you'd better have the 0 vector. Okay, so here's a set that contains what looks like a 0 vector, but it's the only thing in that set. Okay, that's the only vector we're allowed to play with. All right, so a vector space has to come with 2 instructions. How do you add 2 vectors in your set together? Okay, I only have 1 toy, so the only sum I have to explain is how would you find the 0 vector plus the 0 vector? Well, I also have to be closed under addition, remember? So the answer that I get had better be from this set, which has only 1 vector. So that better be the answer, right? And that kind of makes sense because in Rn, 0n plus 0n is 0n. Okay, so this makes total sense. If you want it to work, 0v plus 0v had better be 0v. There can be no other answer. Okay, you can't just say, I passed, let's just ignore that. No, it better have an answer. So similarly, if you take the 0 vector and multiply by any scalar r, I need to tell you how to do it. What should the answer be? Again, by closure, it can only be the 1 vector in our set. And of course, that should look familiar to you, except in chapter 1, we had to prove it. Remember that? If you have the 0 vector 0n in Rn, when you multiply by r, you have to get the 0 vector also. Okay, we had to prove that. It wasn't an axiom, it was a theorem. Okay, so in this case, if I want this vector space to work, then this should be the answer for 0v times any scalar r. What about negatives? Who could be the negative of the 0 vector? Well, it has to exist, right? It has to exist. And again, there's only 1 vector in our space. So the answer had better be, again, 0 vector. Did I mention this is a trivial vector space? Trivial means easy, way too easy. The answer is always a 0 vector. It's almost like, why bother? Okay, but the point here is that it is a vector space, and it is the smallest example of a vector space. There are a bunch of other properties we still have to show. Okay, does it matter if you change the order? Oh wait, you'll get the same answer. 3 vectors, associative property. Oh wait, it's always 0 vector. R plus S times a 0 vector. Oh, the answer is always a 0 vector. So if you work out all of those equations, the answers on every part of those equations is the 0 vector. 0 vector equals 0 vector. So all of those other properties are satisfied. All right, so now we come to one of my favorite examples in the book. Okay, So this vector space, I call it R plus, right? So they're the set of vectors that we write as X with an arrow on top as usual, except that X has to be a positive real number. Okay, X is a real number and X has to be positive. Okay, so 3 with an arrow on top is a vector in R plus. Okay, 3 without an arrow on top, no arrow on top, is a scalar. It's just an ordinary real number that happens to be positive. Okay, what about, let's say, -4? -4 had better be a scalar. Okay, it can't be a vector. I can't just put an arrow on top of here because what is under the arrow has to be a positive number. Okay, so yeah, if I put -4 and then put an arrow on top of that, yeah, still not allowed. Okay, so -4 has to be a scalar. You can't put an arrow. I need to give you two instructions, two sets of instructions. How do you add vectors that look like this together? Okay, so in other words, what is the vector 3 plus the vector 7, for example? Okay, the answer is not 10. What? The answer is 21. Okay, but we have to put an arrow on top. Okay, so I have to go into my arrow box, which is over here. It's off the screen. I have to put this arrow on top. Okay, so that is the answer to what is the vector 3 plus the vector 7. You multiply them together. Does it matter if we change the order? What is the vector 7 plus the vector 3? It's still 21. 7 times 3 is still 21. Okay, so now to mess with you, I need to show you how to multiply a vector by a scalar. Okay, so what is the scalar 3 times the vector 7? It's not 21. Okay, what? It is the vector 7 raised to the power 3. Okay, I can do 7 squared, that's 49. What is 7 cubed? It is 340. Okay, so I'm going to erase that, and I'm going to put the arrow on top. Okay, so it is the number 7 raised to the power 3. Okay, so I can now give you the general instructions. Okay, what is x plus y? Okay, so x, and then, oh, I need the times, the plus symbol. Let me borrow. What is x plus y? It is x times y, x multiplied by y. You put an arrow on top. Okay, we have to worry about closure, right? That's the first thing we need to worry about. If you define vector addition in this way, do I get an answer that looks like this? Okay, well, if x and y are both positive, their product is also positive. Okay, so we can safely say that that answer really is from R plus. So we have closure over here. Okay, so what about scalar multiplication? Okay, what is R times x? Okay, so I will borrow the times here. I forgot, they're also down here. So what is R times x? Okay, so we said take x to the power r. Okay, and put an arrow on top. So there you go. So again, closure. First thing we have to worry about is closure. If x is a positive number, can I define x to the power r even if r were negative? Okay, 7 to the third power, that's perfectly fine. Okay, so let's do a few more examples because, check it out. I got these over here. Okay, so what is the vector 9 times the scalar 2? Okay, so it's 9 to the power 2, and that is, of course, 81. Okay, put an arrow on top. Okay, what if you switch it around? What if it's now the vector 2 multiplied by the scalar 9? Okay, so yeah, and note, there is no arrow on top of the 2. You don't multiply vectors together. Oh wait, but we have a dot product. Coming later. Okay, not yet. Coming later. So what is the vector 2 times 9? Okay, so we said, stop the instructions. 2 to the 9. Okay, and because I studied computer science, I know that 2 to the 10 is 1024. So 2 to the 9 is 512. So 512, put an arrow on top. Okay, so far, all the answers are positive. Okay, what about 9, back to the vector 9, times the scalar negative 2? Okay, again, follow the instructions. Just follow the instructions. So we are supposed to get 9, there we go, 9 raised to the power negative 2. Okay, what does an exponent which is negative supposed to mean? Take the reciprocal, right? So you can write this as 1 over 81, and then you put an arrow on top. And in all honesty, I'm not sure if the arrow will cover that entire. Yeah, oh, goody. Try that before. Okay, 1 over 81 is a positive number. We can put an arrow on top. Okay, now for the coup de grace, what about the vector 9 times negative 1/2? Okay, do we know the meaning of 9? Here I go again. Do we know the meaning of 9 raised to the power negative 1/2? Okay, so we know that the negative exponent means a reciprocal. So we have 1 over 9 to the 1/2. And you know what the 1/2 means? I'm sure you do. It means square root. Okay, square root of 9 is 3. Okay, so we have 1 over square root of 9, 1/3. Okay, so the answer that we get is, let me see if I can just recycle this. Yeah, there you go. 1/3. Closure. Is that a positive number? Yes. Okay. So this power, x to the power r, will always be a positive real number. Okay, so therefore, we know that scalar multiplication is close. Okay. Now, I did say that this is one of my favorite examples, and I want you to enjoy it in the book. I'm going to stop this example right here, and I will let you finish reading it. Okay? So, is there a zero vector? Maybe there is no zero vector. Oh, and then it will be game over. Because you can't put an arrow on top of 0. X cannot be 0. It has to be greater than 0. And if there's no zero vector, there can't be a negative, because how will you add up to the zero vector when it doesn't exist? Okay, So I'm going to finish. I'm going to let you finish reading this example. All right, now once that we have verified that we are in fact dealing with a vector space, then many of the theorems that we saw in chapter 1 will still be valid for these vector spaces. So, for example, the zero vector in a vector space has to be unique. Okay? What makes it unique? If z is another vector that satisfies that if you add it to some vector v, and then you get the same vector v for all v in your vector space, then z has to be the zero vector. Okay, so that's like the real number 0, right? If x plus z equals x, who is z? Ooh, I think I may have just given away the proof to you. Okay, what about additive inverses? They also have to be unique. This means that if v is from your vector space and n is another vector that satisfies v plus n is the zero vector, then n has to be the negative of v. Okay, so again, this should sound familiar because I'm pretty sure it was a homework problem in section 1.1. Okay, so in particular, how do you find the negative of a vector? You can just multiply the vector by the scalar -1, and you should get the negative of v. Now, we have 3 theorems that really make up one important theorem, and that is the zero factors theorem. Okay, so what can we say? Take any vector v in your space. When you multiply by the scalar 0, you'd better get the zero vector. Okay, take the zero vector in your space, multiply by any scalar r, you'd better get the zero vector as well. Okay, now we put them together. Except there's one more piece in the zero factors theorem that needs to be proven. Okay, so for all vectors in our vector space and for all real numbers r times v is the zero vector if and only if either the scalar is 0 or the vector v is the vector v is the zero vector. Okay, so these 3 theorems are part of your homework, and you're only allowed to use the 10 axioms of a vector space. And that should remind you of the instructions in 1.1 that you're only allowed the 10 properties in that theorem in section 1.1. All right, so because of this, we also get to define the meaning of parallel vectors. Okay, so it's basically just an extension of what we saw in section 1.1. Okay, except there, our vectors were visualized as arrows. All right, now our vectors are polynomials, so they have graphs. Oh, they're just flat lines. The zero vector is just, okay, so they're not arrows anymore. Okay, but the definition there worked. It worked for Rn, so we also want it to work for any abstract vector space. Okay, so suppose you have 2 vectors in a vector space V. We will say that U and V are parallel to each other if we can find a scalar A or a scalar B, so that U is A times V or V is B times U. Okay, now we already said that the zero vector multiplied by any scalar gives you a scalar vector. Okay, so we will say similarly that the zero vector is parallel to all vectors vectors, because if you multiply any vector b by 0, you will get the vector 0 vector. Okay, so on that is our video for today. I do hope that we succeeded in opening your mind just a little bit, and hopefully it will open a lot more over the next coming videos, because we're going to start generalizing many of the things we saw in chapter 1. Okay, so what is a linear combination? What is the span of a set of vectors? What is a linearly independent set of vectors? And so on. That's what's coming up soon in our next video. All right, so until then, this is Truth Socrates signing off. I hope you enjoy the rest of the video.